want to, if we can, minimize those side effects, because even though we might have them, to make them even less would be good. So, we know that in the general population, how many kids get a loss of appetite with competing medicines like Prevnar? It's known after years of study, Eric, that 13.5% using similar medicines have some kind of loss of appetite. Does that have a margin of error?
No.
Essentially not, correct?
Pretty much zero.
Good, pretty much zero. Thank you, sir. Pretty much zero. We can assume that that 13.5% does not have a margin of error and is arguably zero. So we're going to build our test around that belief that 13.5% is the status quo. Okay, so what do we do to test our drug?
710 randomly sampled infants.
We gave 710 randomly sampled infants Prevnar and then tested them for appetite loss. Right? Appetite loss. What happened?
121 extreme loss.
Good. And at this point, it's not so much important in this class as it is in your other survey methods classes or your lives. What's one question you should ask right now? And this is not a 244 question. This is almost a pre-243 question, believe it or not, or just a critical thinking kind of consumer question.
What classifies as loss of appetite?
What classifies as loss of appetite in an infant, right? Right? You have to make sure, and I've intentionally taken a lot of that out of these data sets that I gave you because I don't want to, we could focus all day on that and pretty much contest any study ever done. And that's often what happens. They'll contest it, they'll say, oh my God, you only had 121, but the way you measured loss of appetite was so vague that a bunch of kids that may have had it got missed. So I just want you guys to always be thinking about that, okay? Always be thinking about what it means. This is binomial. They either do or don't have a loss of appetite, but you have to question how it was classified, which bin they went into, if that makes sense. Is that fair? So always ask yourself those questions. I don't test on that all that much in this class because I'm working more on the nuts and bolts of what makes a test. So 99% of our work is done because the data comes back as p hat is 121 out of 710. And we go, okay, we can test that. But you have to understand how much energy and effort goes into that 121, let alone the 710 to actually collect the kids for the study. You see what I'm getting at there, friends? So those are the kind of questions. Always ask, what defines loss of appetite? How did you measure that? Did you ask them, are you hungry? Are you not hungry? That's the worst possible way to measure it. Because different kids are going to react different ways. I mean, my son, he's always hungry, probably because he's part of me. But that's the idea, is you have to have some kind of standard of measurement. Probably, hopefully something physiological that can be measured and not queried from a kid. How do you feel today? Yeah, kind of a thing, right? Okay, good. What does this p hat come out to be? Ish. Say that again. 17%. Thank you, Danielle. Well, hell, what does that look like? What does that look like? Remember, why are we testing Prevnar? To see if it's different than the general population. So the variable we're interested in testing right now is little p. And this is going to be the proportion of kids, let's put prop, I think you understand what that means. Percentage, that's even better. Percentage of those on Prevnar who get loss of appetite, who experience loss of appetite. That's what we care about, right? We know that kids experience loss of appetite as a side effect of competing medicine. Is Prevnar any different than the other medicines that average 13.5%? Now, you see how I put different in bold italics? I didn't say test to see if Prevnar is greater than or is less than. I just said test to see if it's different. When you see different, and many statisticians, and you'll understand as we go through the course why this is, many statisticians will always run what are called two-tailed tests versus one-tailed tests. This is a two-tailed test. We're trying to see if the proportion of kids on Prevnar getting sick is different than 13.5%. In other words, going into the study, I don't have any kind of a belief about where it's going to go. I don't know if it's going to be less, I don't know if it's going to be greater, I just want to see if it's different. And this is the kind of test that will identify that difference. It will additionally give us the direction of difference, if there is one. But for starters, it just tells us if there is a difference. And it will tell us, should we go back and do some more testing maybe? Possibly do some more testing. Possibly do some more testing. Well, answer that question.
I don't see why you do a one-tailed test if your sample
Came back higher.
came back higher.
Why not? Here's the deal. Many times the hypotheses are set before the test is run. So you're just going to say, let's look for a difference first. Then if we get a difference, we can retest and see if the significance still holds. And FYI, that's a bit of a spoiler alert. We know it will. And I want to come back. Can I give me like 5 minutes on that question? Or it's even better? Great question. You hear what Will's question was? You knew it was 17%. Why not just test that it's higher? The point is sometimes you don't have a theory going into a study. You just want to see if the status quo has changed, but you're not sure which way it changed. A two-tailed test is the perfect way to test this, for 2 reasons, one of which is just that. The second, which is not obvious yet, I'm going to address it in 5 minutes though, Will Dave. We're going to answer that question. It's a fantastic one. So here's the deal. Here's the deal. Here's the null curve. We're testing to see if it's different than 13.5%. That means the status quo is that it is 13.5%. Remember how I told you before, when it's a one-tailed test, this can be written as greater than or equal to or less than or equal to? This one is just equals to, isn't it? Because it's the opposite of does not equal. It's the opposite. So, what this is going to look like is a classic confidence interval. You still have your 95% built around 13.5%, which is essentially this guy right here, 0.135. You still have that built around that. But now, you're going to have 2 critical values, one symmetrically on each side of that. And Cassie Moore knows what they are. What are these guys down here? They're up there. You told. They're the 2s. A -2 and 2, right? -2 and 2. That gives you 2 standard deviations. Because now, we don't know if it's higher or lower. We're just trying to see if it's different. We're trying to see if it falls here or if it falls here. There's a 2.5% probability down here and a 2.5% probability up here. There's a point in there. So in other words, it's the same area, it's the same confidence interval, but it's symmetric versus asymmetric. But it still occupies the same level of logic as 95% confident that we're in or 5% significance that we're out. Is that fair? You guys buying that? Good so far? Okay. So now we collect our data, which is, like I said, the lion's share of the work is collecting the data. We've got data tests. Our next job is to find out what the test statistic is and what the p-value is for this. Please use your technology. Please don't do these by hand. Please. You can if you want. I just don't think it makes any sense to. I'd much rather focus on the interpretation of what you get when you're done. That's what I always care about. Let's crunch. That test, one prop z, as always. Reset up your machine with your given variables, 0.135 for your hypothesis you're testing against. Successes, 121 out of 710. And grab does not equals. Grab a two-tail. Two-tail is does not equals. We're not being specific. We're not being specific as to exactly where we're going, whether it's up or down. This will handle both of them. Shall we? We shall. Go ahead and draw it. Of course, I should have moved to what was calculating. There we go. What do you guys think? Based on that, you're the FDA. You got to make a call on the side effect label on this thing. What do you think? Do we put a label on this so the side effect might be increased loss of appetite over competing medications? Actually, FDA can't do that. They can't bring somebody else's medicine onto your label. But would you have to put a side effect label on here that says that there's a potential loss of appetite? Danielle's saying, yeah, I don't do that back there either. How come? What's that? Why not? Good, why?
You don't want them to have negative side effects.
So you're telling me that this is implying that it's even gotten worse from normal medicines? What tells you that? Thank you.
Higher
Look at your test statistic, 2.76. Z equals 2.76. That is over here somewhere, isn't it? To the right of 2. 2.76. What's the p-value? You see it right there. It's less than 1%. And definitely less than 5%. Definitely less than 5%. So the question I have for you is, what hypothesis do we believe? What hypothesis do we believe? And while you're thinking about that, I'm going to finish this one. Infants are different rates of appetite loss. What hypothesis do we believe, friends? H0, H1. 1. Does that agree back there? Danielle, agree with me from a parental point of view? Yes. I'm not giving my kid that medicine. I would give my kid that medicine maybe if we landed somewhere in here, which would mean that if it works better than the other medicines and there's no difference in appetite loss, why not? But this is one of those things, I'm not even sure if it works better at meningitis fighting, but it appears that it's very different in the loss of appetite category. Because if it were the same, statistically the same loss of appetite, we should have fallen in here, right friends? But we didn't. We fell out of here. Could we be wrong? Could it be no different than every other medicine? Could we be wrong in our test?
No.
Of course. What kind of error could we have made? What kind of error? Hold that thought. Hold that thought. Let's come back. Let's come back. Let's come back to it. Maybe we jumped the gun on that one a little bit. Hypotheses, test statistic, p-value. What's the conclusion, friends? What would you circle? If you were given that statement right there, what would you circle? It appears or does not appear infants on Prevnar experience different rates of appetite loss than infants on competing medicines. We got 1 vote for appears, 2 votes for appears. Row 3 has Jack. All in favor? It appears Prevnar. Good. Okay, all opposed? We need discussion? Yes, we need discussion. Could we be wrong? I agree. It's got to be it appears because we believe this. But could we be wrong? What type of error could we make on this one? It's the same type of error you're always going to make with a small p-value if you act the right way.
False positive.
False positive type
1.
1. What's the chance of a type 1 error? Every time. Every time.
5.
Always 5%. We're operating 95% confidence here. It's got to be 5% because Cassie's cutoffs, -2 and 2, assume what's in here. What percent? Actually, well, I said once. That's a very vague thing to say. Excuse me. Excuse me. You fucking bones. What's between -2 and 2? What percent? 95. So there's a 5% chance we got data that actually belongs in here, but we just got deviant data. We just got deviant data. That's why it's a potential error. We can't be 100% sure that this Prevnar actually jacks up appetite loss. It might be that it doesn't, and we just got one of those, we rolled 6 5 times in a row or something like that on fair dice. It could be that. It could be that. It most likely isn't, but it could be that. Is that fair? Now, Will asked a very good question about 5 minutes ago. I actually timed that pretty well. What was this question? Do you remember? You can say no if you don't. Totally fine. What was the p-hat value for our study? And 17% is what compared to 13.5%? It's higher, right? It's 3.5% higher. And as statisticians, you're thinking, holy crap, it's 3.5% higher. 3.5% is bigger than a lot of margins of error in studies. So that should be significant. And not only should it be significantly different, it should be significantly increased. So the question is, could we run the test again as a one-sided test? As a one-sided test, and refine our hypothesis to not just say that Prevnar's infants have a different rate of appetite loss, but they have an increased rate of appetite loss. Could we run it again? Will, go ahead.
I guess the thing that seems weird about that is the T-tailed test is kind of a higher burden of proof.
It is, and that's exactly why they do it. Thank you.
But it tells you something less specific than the one-tailed.
It does, but if you can get a higher burden of proof, success rate, you showed, if you will, more significance. You actually proved that. Remember how I said there were 2 reasons to do it? One, is it gives you just a change, a raw change, and then you go for a direction. But the higher burden of proof is actually exactly what it does, and this is why a lot of statisticians use the higher burden of proof, and then they simply look at the sign of the test statistic to speak of the reaction direction. Thank you. That's exactly what it is. So what you would look at is you said the test statistic is positive. That means it's higher. Go ahead. Go ahead. Go ahead.
Then you get into the problem of, you can say with confidence that there's a statistically significant difference.
Yes.
Or that there's more appetite loss.
Yes.
But you can't say it does not equal. You know what I mean?
If you do a one-tailed test.
Right.
Yes, exactly.
Depending on your sample.
Absolutely. Absolutely. No, the higher burden of proof, that's great that you nailed that already after only seeing a couple of these. That's exactly why many statisticians do two-tailed tests. It's because it is a higher, if you can show it works for a two-tailed test, it will always work for a one-tailed test. And that's what I was getting at before when I said, could we redo this hypothesis test with one tail? The answer is yes. And it would come back with the exact same results. This would be this. This would still be 2.76 because it still lands out there. But here's what changes. This actually gets even smaller. Because it's a one-tailed test, the p-value only goes one way. This p-value, it's too hard to see up there on the screen. We'll see it more when we get less significance. The p-value actually shades both ways for a two-tailed test. This guy will actually be cut in half, so it becomes more significant. The converse is not true, though. You can't go from a one-tailed to a two-tailed and always get significance. So, Will, you nailed it with burden of proof. That's exactly why it's often done, burden of proof. It's a higher burden of proof, so if you can succeed with two tails, you can definitely succeed with one. Thank you. That's exactly right. It's more of a classical view. It's not used as much anymore, but it is still used in literature occasionally for that larger burden of proof. Yeah. Thank you. Perfect. Is that fair? If you didn't get that burden of proof, but don't worry. We're going to keep going back to that. We're going to keep going back to that. There is a reason why many statisticians will only do two-tailed tests. We'll come back to it. Yes? Is that okay? Let's do another one. So I'm going to Florida tonight. So let's check the Gainesville. I'm actually going to Gainesville tonight. Gainesville Sun. Go ahead and read this little article down here about the Gainesville